Okay, we are now doing chapter 3-2, and this is recording number 1. All right, so at the risk of stating the obvious, or at the risk of repeating myself, so many times we have this huge pile of data, and we need to be able to describe it, we need to be able to summarize it, and so forth. So in section 3-1, we talked about measures of central tendency. On average, what does this data look like? So that's an important point, okay? And also, another important point is to talk about what is the shape of the data? How dispersed is it? Is it spread out, or is it all concentrated right around the mean? So when we talk about something being dispersed and how much is it varying, typically what we're saying is how much does it vary, how different is it from the average. Okay, so we're going to spend a little bit of time on this first example, but because I think this first example actually illustrates this concept very well. So to start with, section 3-2, the author says that in statistics, in the science of statistics, to describe the data set accurately, statisticians must know more than just the measures of central tendency. So here's an example. We're talking about outdoor paint. So we've got brand A and brand A and brand B, and we have here's the results. Here's our data. Now, there's only 1, 2, 3, 4, 5. There's only 6 data points here, right? So for each of the brands. So it really isn't that many. But imagine, if you will, if you had tens of thousands of data points, okay? Then it makes it more, you can see the motivation for why we're doing this a little bit more clearly when we have tens of thousands of data points rather than just 6. Okie dokie. So we've got these two experimental brands of outdoor paint, and we want to find out how long do they last. Okay, we want to have some idea about which is the better paint. Okay, so you make the 6 gallons. We have these are two small populations. We're not looking at a sample from each population. This is the population, brand A and brand B. Okay, and then we do our painting, and then we find out in the results in months how long does the paint last before it fades away. Okay, so the mean, so it's going to be mu because we're talking about a population now. The mu for brand A is, what do? We add these guys up. We add up 10 plus 60 plus 50, add them up on top, and then in the denominator is the total number of data points. So we got 35 months. The mean for brand B, you add these guys up, and for heaven's sakes, it's the same number. It's 35 months. So you would be tempted at this point to say, well, on average, they last the same amount of time, so there's no significant difference between them. Either one is just as good. Well, that's not true, because sometimes what you're really concerned about is the variation. Okay, how you could conclude that they last equally well, but when you examine them graphically, a different conclusion might be drawn. So brand A, if you put this in kind of a little graph form, a little graphical form, what would you find out is that it is all spread out, whereas in brand B, everybody's, the average is 35. In brand B here, the smallest amount of time that it lasted was 25. The greatest amount of time was 45. So it's kind of all centered in here. It's not spread out. It doesn't vary very much from the mean, which is 35. Whereas in brand A, look what's going on here. This one is as low as 10 months and as long as 60 months. That's probably not a good idea, right? You don't want to have a paint that might only last for 10 months, right? Okay. If you're in the nursing business, or if you're a nursing student, another example for this might be medications. If you take a certain medication, what's the average heart rate after you take the medication? Well, you may have 2 medications that give you the same average heart rate or pulse rate, but the variation is so significantly different that your doctor would be very concerned about giving the medication, because you don't want to have a great deal of variation away from the mean. You don't want to differ from the mean so significantly. Okay, so we can easily come up with examples. The exercises have plenty of them, of where this might be something that we would be interested in. Okay. All right. So how do we measure this? We got to come up with some mathematical way of measuring this. We can't just wave our hands at it and draw pictures. Okay. So what do? So this concept of the spread, otherwise known as the variability of a data set, we have three measures that we commonly use: the range, the variance, and the standard deviation. So we're going to talk about all three of those in this section. Okay, the range is the simplest one. It's just the highest value subtract the lowest value. So we call that the R. That's the highest value subtract the lowest value. So if you look at the example here, for brand A, it goes from 60 to 10, so that's 50 months. Brand B, it's 45 to 25, so you subtract and you come up with what that, it's called a delta, D-E-L-T-A. The delta is the difference, okay? All right, so we got a delta, or the range here, of 50 months compared to 20 months. It may very well be that you don't want to have so much of a delta. You don't want to have that big of a range, because you want your product to be more consistent. You want your heart rate to be more consistent. So that would be a measure of something that you would be interested in. The bad news here is with range. The reason the range is not commonly used is because if you have an outlier, you remember what an outlier is an extremely high or an extremely low data point, okay, or data value. It can affect the range significantly. So here's an example of that. So again, it's the Bill Gates walks into the room. One data point can affect the range too much, so it's not as useful as the other ones are. Or you have to just be smart enough to toss out that data point and don't consider that data point. Okay, so he talks about that here. Okay, so now let's talk about variance and standard deviation. Okay, so this is where we're going to start talking now about you have a population variance and you have a sample variance. They're two different things, okay? Remember, the population is what you're interested in, the big picture. All of the students at Riverside Community College District, all three campuses. A sample is a subset of the population. We are going to need to know how to calculate the population variance and how to calculate the sample variance. There's two different techniques. They're slightly different formulas, okay? As far as variance compared to standard deviation, that's not hard at all, because the standard deviation is just the square root of the variance. Now, you'll see later on, some formulas that we use will use the variance and some will use the standard deviation. So you absolutely need to know the difference between them, but it's a very simple difference. The standard deviation is the square root of the variance. Okay. All right, so what do we mean by variance? Okay, we need to know what data variation means. It's the difference, or it's the distance each data value is from the mean. So when we're talking about variance and standard deviation, we're talking about how different is, on average, how different are the data points, okay? Is based on the difference each data value is from the mean. And what you're going to do is you're going to take all of those differences, and you're going to find the average of that, and that's going to be the variance. Now I say that's a very, very bird's eye view picture. That's not exactly what it is, but that's the essence of it. The essence of it is it's the average of the differences. The problem is that you'll see here in a minute, we have to square the differences in order to get rid of the negative values. So it's the difference of the squares, or it's the average of the squares. It's the what we in engineering we call that the root mean square. It's the square root of the mean of the squares. Okay, RMS, a very common abbreviation. Okay, so let's get into it. It's easier to just do the calculation than try to use the words. Okay, so in the outdoor paint example, the mean for brand A is mu of 35 months. A specific can, let's say for example the can that lasted for 50 months, the deviation is, how much is the deviation? It's x take away mu. So 50 take away 35 is 15. So the deviation for that particular data value, for that particular data point, is 15 months. Okay, so if you find that if you take the sum of these deviations, it's always going to add up to 0, which is kind of boring, right? I mean, that doesn't help us. And let's take a look here. Okay, so so like this data point here, 50 take away 35 is 50 take away 35 is 15. Okay. Okay, so that's the x take away. How does he? Let me see how he writes that. Give me 1 second here. Yeah, x minus mu. All right. So the data point is x. So 50, x minus mu is 50 take away 35. Okay, well, how about over here? X minus mu for this guy is 20 take away 35. That's negative 15. So negative 15. So here you have 50 take away 35 is 15. Here you have 20 take away 35 is negative 15. Add them together, and what do you get? You get 0. So each one of these is kind of paired with the other, and unfortunately, you're going to always get 0. So that doesn't help us very much. It doesn't help us to try to come up with a measure that always ends up with being 0. That doesn't give us any value, okay? All right. The sum of if you just take the sum of the deviations for all the data values about the mean, this sum will always be 0. Okay, so summation of x take away mu is equal to 0, and then do it for yourself, and you'll see why that works out. So how do we avoid this problem? Well, there's a couple of ways we could do it. One would be to take the square root, or excuse me, we'll take the absolute value. If you took the absolute value, you wouldn't have this problem of adding up to be 0, right? You'd have 15, instead of having 15 plus negative 15, you'd have 15 plus 15. So that's one way of doing it. But the way we choose to do it, the standard way of doing this, is you take the squares. That gets rid of this problem. So to eliminate this problem, we sum the squares. We don't sum the actual deltas here. We don't sum the deviations. We sum the squares. So it's x take away mu quantity squared. Okay, and then we find the mean of these squares. So that's what I was saying before. You're finding the mean of these deviations, but not exactly. It's the mean of the squares of the deviation. Okay, and how do we do that? Divide by n. That's the total number of data values. So symbolically, this is what it looks like, and this is called the population variance. Now, here's a weird symbol for you. The way you pronounce this little symbol here is sigma. So it's sigma squared. If you have to say it, that's what you would say. You'd say sigma squared, or you would say, just use the words population variance. There's a little bit unfortunate notation, but we're kind of stuck with it, okay? So sigma is the symbol for the Greek lowercase letter sigma. So this is the uppercase, that's a sigma there. This is also a sigma. This is the lowercase, this is the uppercase. Okay, so since this measure is in square units and the data are in regular units, what we normally do is for most purposes, we're going to take the square root of this variance. Okay, so we call this the variance. We can take the square root of that, and we're going to call that, for a variety of reasons, the standard deviation. So the population variance is the average of the squares of the deviations. Okay, here's the formula. The standard deviation is the square root. So it's the root of the mean of the square. So that's why engineers will say it's the root mean square. That's what they're referring to when they talk about this sigma. And the root mean square is very useful in a variety of contexts. Okay, so in any event, now we have the formula for this. Is this a formula? You just crank it out. You just plug in the numbers and crank it out. We'll see later on how we're going to use it. So I'm out of time, so that's the end of this recording.